so in today's class we are just going to look at a couple of other types of mixers and then we'll look at TX architectures. Okay. Okay. So the first kind we'll look at are called potentiometric mixers. Okay. So the basic idea is very simple. So you take a MOSFET. Okay, and you can look at the RDS of the MOSFET, and you're going to try to make the RDS a function of the RF voltage. Okay, you're going to try to make this inversely proportional to VRF. Okay, so that if you look at your IDS, and if VDS is a constant, you can make this proportional to VRF. Okay. Okay, and obviously if VDS is a function of, if there is directly proportional to the LO voltage, then right, very simple idea. So you are going to bias the transistor in the linear region and try to make its RDS inversely proportional to RF. Okay. Okay, so let's look at the mixer. Okay, so this guy. Sorry, VLO minus. This VRF plus. This is also VRF plus. This is VRF minus. Okay, and I'm going to cross connect these two guys. Your IF output goes like this. Okay, this is basically to convert the current to voltage. You have two more capacitors CV. So M1 So the 4 transistors, M1, M2, M3, M4, and of course the currents are I1, I4, I2 and I3. Okay, these 2 currents flowing out, we're going to call it IO, this is IO2 and this is IO1. Okay, so what we have tried to do here is to, so if you look at just the front end, just the 4 switches, so they'll be operating at your RF frequency, so your multi gigahertz frequencies. If you look at the op amp, it's going to be operating in the megahertz range because you only want to transform the output, which is the IF. Okay, so what do you know about the op amp? You know the input is has a virtual ground, right? The 2 inputs, but then beyond its unity gain frequency, it is not a virtual ground anymore. So you're helping things along by adding these capacitors. They'll create a signal ground, okay, at higher frequencies. And both CV and CF will give you some attenuation of high frequency components, because obviously since you're multiplying VRF and VLO, you are going to get LO plus RF, LO minus RF, you might get LO feed through terms, okay. So you'll get bunch of terms, you're going to attenuate those using these 2 filters. It's a second order filter, okay. Okay, so let's look at the 4 currents. So I1 is beta 1 times, look at 1 VRF plus, okay. Okay, so what we'll do is we'll say that the DC voltage here is some VLO DC. Okay, let's see, have I missed out anything else on the picture, on the figure? Yeah, that's it. Minus VT1, and it's in the linear region, right? So minus VDS by 2, whole things times VDS. Okay, similarly you can write I2, so it will be VRF minus okay, and similarly you can write I3 and I4, okay, in terms of the currents and voltages. Okay, and this happens to be a double balance structure. Okay, so what will happen is all your LO feed through terms vanish as long as the transistors are well matched. Okay, all your, if there are any nonlinearities due to, let's say, GDS of the transistor, if it's not a perfectly triode behavior, that will get cancelled to a first order. And we'll look at, if you look at IO2 equals I3 plus IO4. Yes, you'll have to set your DC point such that it happens. That happens. It should be very linear. Okay, so the thing is, what will happen is the more you bias it in the linear region, the better your transfer characteristic will be. Okay, and your IAP3, it will matter for your IAP3. Okay. And what is V out plus V out minus? Let's just look at the low frequency term. Let's say this is VIF, right? So this is nothing but RF. Okay. Give me a second. Okay, and this happens to be beta times the signal VRF plus minus VRF minus. times okay. So this is what we wanted to achieve. We wanted to get a product of the RF and the LO terms. Okay. So you can get extremely high IIP3s, okay, somewhere around like 40 dBm, which is really good, right? Because the IIP3s we have been looking at maybe like 10 dBm, 20 dBm, something like that. 40 dBm is quite good, okay. But if you look at the noise figure of this guy, it's actually very high. Can be as high as 30 dB. Okay. Main reason is because your input MOSFETs are no resistive. So all that resistive noise adds right at the front end. Okay. So what happens is the noise figure can be quite high. So in the end, if you look at the dynamic range, so the dynamic range is what you're interested in. Okay. It turns out to be almost the same as a Gilbert mixer. So if you're going to end up using this, you can get the same performance if you add more gain at the front end, right? And use a Gilbert mixer. Rather, if you add more gain to this, you can get the same gain and same IIP3 performance as you would with a normal single stage LNA and a Gilbert mixer. Okay? Okay. Next, we'll look at another mixer structure called the passive mixer. Okay. What have we done so far? If you look at all, yes. No, noise figure is always in dB. Yes. Yes, it is a very high value. Yes, it is a very high value. So that one is almost, that is the input noise, it completely drowns out the input noise, that's what it means. Okay. So, so that's why you won't find a lot of people using, the potentiometric mixer, except in probably very, very niche applications where you're interested in linearity. Probably noise is not a big concern. Okay. Okay. Next we'll look at the passive mixer. So what have we done so far? So far, what all the mixers we have looked at, we have taken the RF signal, converted to, using a transconductance to an RF current, and somehow used the RF current to, even in this case, right? We have tried to convert it to a current and then we are converting to a voltage, right? So what the passive mixer does is it directly sends your directly works with the RF voltage. Okay. So let's look at the architecture. Actually, so this is a double balanced passive mixer, okay. And then you're going to take the output across a capacitor CL. Okay. So what happens to this guy? So if you look at the first half cycle, so this guy is conducting and this guy is conducting. Okay. What is V out? This guy conducts, you get plus VRF here, minus VRF here. Okay. The second half cycle, we have this guy here, this guy here. So it's minus VRF. Okay. So if you look, oh man. Okay, so if you look at the overall transmission, right? So it's as if your output RF, right, is switching between plus and minus RF at the rate of the LO, right? or rather let's do it this way. Okay, where right, it's switching between plus or minus 1. So it's as if you are multiplying your RF with a signum function which is at the rate, of course, at TLO. The rate is TLO. Right? And we already know what the gain of this thing is, right? We've calculated the Fourier series of the signum function. The gain of the fundamental is 2 over pi. Remember that, right? So the conversion gain is going to be 2 over pi. So which happens to be approximately minus 3.92 dB. Okay. So in other words, it actually has a loss. It has a conversion loss. But it's not a problem. It so happens because as long as your noise figure is held in check, you don't mind having some loss. You can always make it up with make-up gain using LNAs. Okay. Okay. But if you look at practical implementations, most of them have so let's 5 to 6 dB loss. I'll put it that way. Okay, because of other non-ideal effects. Here we have assumed it's a perfect switch. Okay, in other cases you can have losses in other places. So it will end up being slightly lower. Okay, another 1 or 2 dB lower. Okay. The other thing is you can show, I'm not going to show it in class, but you can show that. So here we have used a square wave LO. If you use a sinusoidal LO, it so turns out that you can actually get higher gain. It seems counterintuitive, but you can get higher gain. Okay. Approximately pi by 4, which happens to be minus 2.1 dB. Okay, you can refer to of Thomas Lee's textbook. Okay. Okay. So now the next thing to do is, so you've added this capacitor at the output. What is the transfer function of the capacitor? It's going to have some kind of low pass response, and again you can show that the transfer function is 1 over okay, where GOAV is the average value of the output conductance, because obviously the output conductance varies over one cycle because the number of switches which are on, the switches turning on, switches turning off, so the actual output conductance will vary. So GOAV is the output conductance at the IF port. Okay. So let's say you want to boost the gain. Okay. You can try to do some kind of L match at the input, which will give you some kind of passive gain boosting. Okay. So if you look at the noise figure of this guy, the noise figure will be maybe 10 or 11 dB, which is still pretty good for the loss you are getting. Still pretty good. IIP3 can be pretty decent. It can be around plus 10 dBm, sometimes higher. Okay. Okay. So the last thing, what else do you know about this? So the switches, you are just using them as switches, right? So you don't have any DC bias current through these transistors. Okay, so you would expect that, remember that your flicker noise is proportional to your DC current in the transistor. Okay, so you would expect that there is no flicker noise in a passive mixer, but it turns out, because it happens to be a time variant system, there is noise folding, so you will invariably have flicker noise in the output. It may be lower than a Gilbert mixer, but you will have flicker noise. Okay, that is something to know. Okay, obviously no DC current means very low power consumption. So it can be an extremely low power mixer. Okay, so we are done with mixers. Does anybody have any questions on any of the mixers? Noise, linearity, anything? Okay, so we'll move on. So the next thing we are going to study is we are going to look at some TX architectures today, and then we'll move on to RX architectures. Okay, we took a very quick glance, right? I think we had half a class or one class on RX architectures. So we'll do TX first, because TX is usually very simple. The reason is, okay, so you are producing, the transmitter is where you are producing the signal. Okay, so typically the signal is strong enough, you don't have a problem with noise. Okay, you don't have a problem with interference, right? You don't have a problem. So the main problems are power consumption, linearity. Those are the two big concerns. Okay, there is a third concern which we'll get to, which is noise does not matter, in-band noise does not matter, but you'll find that out of band noise matters. Okay, so let's look at TX architectures now. Yes. Yes. Because in one case you are specific. So in one case you are just you want to make the switches extremely low resistance. You want to make it zero. You don't expect the resistance to vary based on the RF voltage. But in reality it does. In reality your switch resistance is going to be a strong function of your LO voltage, for example. Okay, so that limits your IIP3. In the other case you are explicitly making it a function of your RF voltage. Okay, because of that you can get much better IIP3s. Okay. Okay, what is also not a problem, you don't care about things like band selectivity. Okay, because you are not in the receiver. In the receiver you are trying to receive, only a small channel, whereas in the transmitter you are transmitting, only a very low frequency signal. Yes. Yes. Okay, so at the receiver you are interested in receiving, so signal values you are receiving are in microvolts. Okay, maybe even smaller than microvolts. Here on the other hand, the signal going into your transmitter from the baseband will be in several tens of or hundreds of millivolts. Okay, you can see the dynamic range difference. Okay, so you are far above your SNR requirement. Your SNR requirement may only be from your digital baseband, may only be like 10 or 15 dB, maybe 20 dB maximum. Okay, so you will be much higher than that. Okay, and remember you are actually transmitting into a background of noise, right? And as long as you transmit high enough power, that won't be a problem. Okay. Okay. So the first kind of this thing is the direct conversion. also called the homodyne Tx. Actually, before we do that, did I yeah, okay. Now before we do that, remember we talked about a band pass signal x of t, right? Can be represented as, so polar form, the polar form is so A of t is the amplitude modulation and phi of t is the phase modulation. You remember this, we talked about it briefly probably a month and a half ago, okay? And you can also represent it in Cartesian form, okay, as xi of t cos omega lot minus xq of t sin omega lot, and obviously A of t cos phi of t is xi of t and A of t sin phi of t is xq of t, okay. Now remember that this signal is actually a real signal, it doesn't have complex components. However, people do talk of what is called a complex signal because remember these are the two things which you produce from the baseband. So you produce an in-phase component and a quadrature component. If you think of it in terms of Cartesian, okay, coordinates. So what you produce from the baseband are in-phase and quadrature, or amplitude and phase, depending on if you have a polar transmitter. You have, of course, we have classes of transmitters called polar transmitters where you work with the amplitude and the phase. Okay, that we won't discuss in this course. But the typical standard transmitter would use I and Q. Okay, so xi of t and xq of t are the signals you are interested in. Okay. So what you want to do is you actually want to generate this. This is the xi of t cos omega lot minus xq of t sin omega lo of t is what you want to generate out of the Tx, because that is the band pass signal coming out of the Tx. Okay. And this goes through a PA. Oops. Okay. So you have a mixer. This is your direct conversion transmitter. So you have xi of t, xq of t, which are the baseband signals. So you're going to send them through two sets of mixers. One mixer, you're going to mix xi of t with cos omega lot. The other mixer, you're going to mix xq of t with sin omega lot, and then you're going to subtract the two to get the desired band pass signal. This goes through a PA. The PA is going to have some kind of matching network at the output because now you're going off chip. Okay. In a typical FDD system, it will go into a duplexer. You go to the antenna, and of course this goes to the RX side. Other side of the duplexer goes to the RX. Okay. Okay, so this is the simplest TX transmitter. It can be used, but there is one big problem. Okay, one big problem is if you look at this guy. So you can, of course, you might need a band pass filter here in some cases. Okay. What does the signal here look like? So it's going to be some kind of modulated signal, and it's going to have very high power. Yeah. Okay. The output of the PA is it's a modulated signal, so it's not a narrow pulse, this thing anymore, pulse in your spectrum anymore. Okay, it's now a wideband signal. Okay, fairly wideband. And yes.
Why do we separate the baseband signals into IN? What's the advantage?
it is not the advantage. In a general modulation scheme, if you have information in both the amplitude and the phase, you will always have an in-phase and a quadrature component, right? There are some cases where if you just do amplitude modulation or if you just do phase modulation, you can get away with just using, a single mixer. But for any general modulation scheme where you have information in both, you can separate the two informations either in amplitude and phase or in I and Q format and send it through the transmitter. Okay? Yes, that's right. We looked at the modulation schemes in the second class, right? So if you see, some of them do have variation in both amplitude and phase with time. QPSK, QAM, there are lots of modulation schemes which do need both. Okay? And by the way, the other thing to note is, let us say you have information not in the amplitude but just in the phase. If you convert it to this form, you will find out that because each one depends on both A of t and phi of t, even if you have information just in this, you'll end up having to use in-phase and quadrature components. So there may be cases where if the information is contained only in the phase, it may be more efficient to do a polar kind of transmission. Okay, and there are, for example, GSM uses like a GMSK so GSM uses GMSK, which has information only in the phase. Okay, there you may end up, it may be more advantageous to use a polar transmitter. But if you end up using an IQ transmitter, you will have Xi of t and Xq of t. Both of them will vary with time. Okay?
How do you generate Xi of t?
That is generated by the baseband. You don't have to worry about it. So the baseband produces signal and gives you, so what happens is baseband produces I and Q signals that is sent through a DAC, and the DAC output comes as an analog form to your transmitter. Okay? In either voltage or current form, doesn't matter.
Baseband will do both phase manipulation and amplitude.
Yeah, baseband can handle everything.
And that will have output is a single signal, or it will have two signals, Xi or Xq?
Yeah, it will have two sets of signals, Xi and Xq. In fact, in general, what you will see is the baseband will typically give you not just Xi and Xq, it will give you Xi and Xq, but each of them will be a differential signal. Okay, so you'll get Xi, Xi bar, Xq, Xq bar, so you'll get 4 lines. Okay? So we know that the PA output is a very high power, so it will typically be like a watt, okay, which is very high. Okay, so what happens is, you have a phenomenon called PA pulling. Okay, what happens is when you are trying to transmit so much power, the PA spectrum, either through electromagnetic coupling or could be through, if they share a common supply, it could be through supply, it could be through the substrate if they are on the same chip. Okay, you could see what is called PA pulling. What happens is, this modulated spectrum will corrupt your pure sinusoid and it will give you a very noisy system. Okay, a noisy LO. Okay. Yes, it is like it is a parasitic feedback, right? You ideally don't want a feedback, right? So it is actually a parasitic feedback through either an EM path which you should be modeling. It could be through the substrate, which again you should model, which is why people tend to try to model as much as possible, because you want to model all of these things. Some of them can be, some of them cannot be. Okay. Okay. So there are some cases, some systems where your PA switches on and off to save power, because remember, if you take a transmitter, PA will be the number one, because it is burning, it's outputting around 1 watt of signal. Okay, the signal going into the PA will be much smaller. So typically PA will be the number one most power hungry block. Okay, so you try to, if you are not using the PA, let's say if you are not transmitting, you try to turn it off. If you look at cases where remember we talked about TDD systems, right, where you turn on the TX and then you turn on the RX, right? You try to switch between the two, right? Cases like that, you might, while the RX is on, you want to turn off the PA. But what happens, the minute you turn on the PA, there will be a huge EM transient which will again pull the VCO. Okay, because the VCO is at a certain frequency, the PA output is at 0 frequency, there is no output, and then suddenly it tries to come up to that frequency. So if you look at the LO, it will just jiggle around. Okay, sometimes the LO is created by a PLL which has locked the VCO to a particular frequency. Okay, what can happen is the VCO can lose lock if the pulling is strong enough. Okay, okay, and of course this phenomenon of pulling the VCO is called injection locking. Okay, so basically what happens is injection locking is you take an oscillator, and if the output frequency depends on the signal coming in through a particular path, it can be injection locking. Typically the main path you want to use is if you have a voltage control oscillator, you have a DC voltage. You would have studied this in the PLLs course, in the analog ICs course, right, when you have PLLs. So you have a DC voltage produced by some mixed signal system, and the DC voltage is what controls the oscillation frequency of the VCO. Okay, if you have a second path, that's usually called the injection lock path. Okay, typically if there is some signal coupling in through a different path and the output frequency of the VCO does depend on this, it is called injection locking. Okay, so what can you do to improve this? The easiest way to improve this is to offset the frequencies of the VCO and the PA, right? Because it so happens that the closer they get, the stronger the coupling, and that kind of makes sense. Okay, so you're going to offset the frequencies. How do you do it? Okay, so one way to do it is okay. So you take two oscillators, okay, operating at omega 1, other at omega 2, and of course you need a band pass filter now. So now this output omega 1 plus omega 2 is going to be produce your cosine and sine. Okay, so instead of having a single oscillator in this case, so in this case this is just omega LO. In this case this produces at omega 1 plus omega 2. Okay, this is one very simple way of doing it. Okay, and obviously then what happens is your omega PA is much larger than omega 1 or omega 2, or quite different. You don't have a problem with pulling. This doesn't matter because omega LO is omega PA, right? It's a direct conversion transmitter. So omega LO is the same as omega PA. Actually what I should have said here was omega VCO is what you want to change, not omega LO. Right? It is generating omega 1. So this point is going to have omega 1 plus omega 2 and omega 1 minus omega 2. You have a band pass filter to create just omega 1 plus omega 2.
That is the omega LO or omega P.
Yes.
And now you are saying that omega P is different from omega 1 and omega 2.
Yes, exactly. So it won't pull. Pulling will be a lot less.
See, on the assumption that the conversion, if we mix these two, the gain, we get some gain.
Okay.
That
But
is,
why do you care about the gain?
I mean, it's a consider entire feedback loop. Because of offset, I get some attenuation.
What feedback loop are you talking about?
This parasitic feedback.
Okay.
So that one, when you offset these two frequencies, because it is like this or that
Mm-hmm.
attenuation.
Mm-hmm. That's right.
And there is a gain here. This gain offsets that attenuation.
What gain do you have here?
Conversion gain.
Actually, you don't care about conversion gain here, right? This is the LO frequency, right? Typically, this will be a several hundred millivolts, right? We looked at cases where there may be active mix. Remember, we talked about how you want to size it. At the end of the day, this is going to have a fixed amplitude, irrespective of which kind of, whether you generate it as omega 1 plus omega 2 or otherwise. And typically, the VCOs which you design will also have a fixed amplitude. They'll be similar. Okay, they'll typically in the VCO to improve noise, right? To minimize noise, you tend to have maximum amplitude coming out of the VCO. Okay, so the amplitude itself will not matter too much. As long as the frequencies are offset far enough, it won't pull anymore. Okay? You can choose, you can choose whatever you want. You can choose omega 1 equals omega. Okay. Okay, let me draw it out separately. So, okay. Let me call this. So, xi of t. Rest of the system stays the same. Okay. Okay, everything else stays the same. The only difference is you have 1 okay. So what this means is that is what you create. You'll have 2 VCOs to generate omega 1, omega 2. Okay. Okay. So the idea is very simple. Okay. Idea is not very simple, but it is the concept is very simple. Okay. So the PA actually has a very large output power coming out of it. Okay. What is going to happen? It is basically radiating that power. Okay. Now it so happens there will be a parasitic path from your PA to your VCO. There are several parasitic paths. Okay. If they share the same supply, that is one parasitic path. Okay. If they share the same substrate, that is another parasitic path. If they are close by to each other, that is another parasitic path through EM coupling. Okay. Any one of these, if you look at the power coming out of the VCO, so the VCO is going to be burning a few milliamps, 2-3 milliamps. Okay. So the actual raw power which is being put into the LO signal is very little. It's probably a few milliwatts. What is coming out of the PA is a few watts. Okay. So if the parasitic path is strong enough, you could corrupt the VCO signal. Okay, that is the idea. And the main thing is, if your PA was just a single tone, it will be less of a problem. The problem is this guy is actually a wide band, so you will start seeing that when that couples to your VCO output instead of being a pure tone will end up having sidebands also. And it's effectively noise for the VCO. Okay? Okay, what else can you do? What is this number? Okay, so what is the other thing you can do? So instead of doing omega 1 and omega 2, having 2 VCOs, what you can do is you can have a single VCO. You can have a frequency divider. Okay, this is actually the most commonly used. So let's say, for example, divide by 2 or divide by 4 is used quite commonly. Okay, so this is now the VCO frequency is now 2 omega LO. To address, why? So actually that's what it depends on, right? So the advantage of course is that it produces 0 and 90. Okay, quadrature signals are directly generated through the divider. Now what you are effectively, let's say if you are using a divide by 2, okay, so if your omega PA is output frequency is 2 gigahertz, okay, your LO frequency is 4 gigahertz, your VCO frequency is 4 gigahertz, LO frequency still remains the same at 2 gigahertz, the VCO frequency is now 4 gigahertz. Effectively what happens is, if there is any parasitic coupling, it is going to be from the PA second harmonic, and typically anyways you try to minimize the PA second harmonic. Okay, so the assumption is it will couple less, it will pull less, that is the hope. Okay, Obviously, as you go to higher harmonics, if you use divide by 4, it will pull even less. Okay? Yes, somebody else had a question? Okay, so the only thing to keep in mind as you are saying is, it's a little bit more difficult because now you are talking about parasitic coupling paths at higher frequencies. So those paths may be actually be stronger depending on the path. Okay?
About having omega by 2 and then multiply.
You want to have an omega LO by 2 and then multiply it. Yeah, you can do that. Yeah, that is the only thing. You can either need a PLL or a mixer. Like I said, this is like a multiplier, right? So, okay, I have it right there. So, if you give omega 1 is omega LO by 2 and this is also omega LO by 2, that automatically gives you LO. So, it is like this. You need to use something like this. Either a mixer or a PLL to multiply it by 2. One of those two things you will have to use. You can do that. Okay? And of course, the fourth kind is a two-step. We talked about direct conversion TX. Other kind is a two-step TX or a heterodyne TX. Okay? You may need a filter here. Okay, you can do this. And of course, you may also need a band pass filter here again. Okay, so first you do, this is your first step, this is your IF, okay, and then you convert again, and omega 1 again, omega 1, omega 2 are very quite different from omega PA. I'll just put it as much greater than, but yeah. Okay. Now, the only thing to remember is, all the mixers we have studied so far produce both of these guys, right, of equal amplitudes. So this DPF2 will have quite strict requirements, because the power levels at this, once you go to the end of the transmitter, they are quite high. Okay. Okay, so the last thing you need to know about transmitters are unwanted emissions. Okay. So what happens is, you are trying to transmit a particular signal. The problem is, since your transmitter is non-ideal, you are always going to transmit something outside the band in which outside the band of interest. Okay, and what happens is, obviously anything you transmit outside the band of interest is going to cause problems for somebody else. Okay, so what happens is, both the standard as well as the regulatory authority has strict rules on what you can and what you cannot transmit. Okay, and typically this is given as an emission mask. It's called a mask, emission mask, and you have to make sure that what you are transmitting lies below this emission mask. Okay, for example, if you take I'll take an example of a GSM signal. GSM modulated signal could look something like this. So if you look at the spectral mask, it will look something like this. So you have to lie below this. Okay. Now obviously, let's say system has a spur, okay, that is going to be unacceptable, completely unacceptable. So you have to do something about it. Otherwise, what will happen is the regulatory authority will not allow you to use the device, will not allow you to sell the device if the device has a problem. Okay? Okay. That's your emission mask. Then you have something called ACP or adjacent channel power. Okay, so what this is so you are trying to transmit in a particular channel and you shouldn't damage the guy who's transmitting right next to you, because that is where typically you will have most issues. Okay, the person who's closest. Remember, you can look at the power is going down as a function of frequency. The guy who's right next to you will probably have the most problems. So they have specs on how much you can transmit right in the adjacent channel. And usually the power levels are still high enough such that will be limited more by linearity rather than noise. Okay? And so different standards will have different requirements. So if you see CDMA calls it ACPR, WCDMA calls it ACLR or adjacent channel leakage power ratio. GSM calls it ORFS or output radio frequency spectrum. So they all mean the same thing. They are basically defining an emission mask. Okay? Okay. Obviously, spurs. Okay? Whether they are produced by the mixers, PLLs, whatever, doesn't matter. We should get rid of them. Okay? And of course, the last one. Remember, we discussed noise. We said that noise is not a problem, and that is true. In-band noise is not a big problem. Okay? It so happens that out-of-band noise can cause issues, especially in FDD systems. Okay? Why? So what happens is, so let's take the case of a PA and this is your LNA. Okay, so what's going to happen is the duplexer is going to have finite rejection from the PA output to the LNA input. Okay, so what's going to happen is, so let's say this is your modulation, right? So I'll show only one half one. So let's say it goes like this and it goes like this. Okay, eventually it's going to go, I'm going to call this the noise floor. Eventually it's going to go below the noise floor. Okay, the modulation power is going to go below the noise floor. Okay, but what is this noise floor defined by? It's defined by the circuits of the transmitter, right? Okay, and so this is your TX frequency, center frequency, and eventually there is going to be a point where you're going to have an RX center frequency. Okay, so the noise of the TX at the RX frequencies in the RX band is going to leak through the duplexer into the LNA input. Okay, and effectively increase the noise floor. Is that clear to everyone? Pretty straightforward. So the rejection will typically be maybe 50 dB or something like that. So the thing is, what you have to define rejection is, you need to define the amount of rejection, okay, power rejection. You need to define the frequency at which it happens. Okay, and that is defined usually by the standard. If you are transmitting at a particular frequency, you are usually receiving at a particular frequency. Okay, so this can be 50 dB, for example. This can be, it is usually in terms of either dBc per hertz or dBm per hertz, one of the two. And once you know the PA output power, once you know the trans TX noise dBc per hertz, and you know the duplexer rejection, okay, you can calculate the power in dBm per hertz which is being leaked to the LNA input. Is that clear? And remember, we had the minimum detectable signal for your sensitivity. We calculated that in class, right? It was minus 174 dBm plus 10 log B plus NF plus SNR min, right? That was a minimum detectable signal, right? So what happens, this minus 174 dBm per hertz is basically your KT noise floor. Okay, that is your received noise floor, right? That's your noise floor of the background system. So now what you have to make sure is the power leaked in dBm per hertz from the TX to the RX should be much below this, so that it doesn't raise your noise floor. Okay, otherwise obviously if it raises the noise floor, obviously, okay, so let's say this one, your noise floor is minus 174. If this leak power is also minus 174, then it actually becomes minus 171. You have just raised your effective noise figure of your overall transceiver by 3 dB. And obviously that's a huge deal. 3 dB is very, very big. Okay, you're effectively doubling your noise. Okay, so typically you want it to be at least 10 dB or even lower than the background noise floor. Okay, okay, I think that's it for transmitters. So we'll continue with receivers next class, right? Okay.